it's my pleasure to introduce the new session at MFEM Community Workshop. So we are going to have lightning talks by our young blood of the MFEM community. And it will be 8 talks, lightning talks. Everyone will have 5 minutes to show their idea on a couple of slides. We are going to divide the session into 2 parts. So first 4 talks, everyone 5 minutes, then we will have 10 minutes for Q&As, and then we will follow for the other 4 talks. And without any further ado, Shani, please go ahead, grab the screen and show us what you have.
You can see my screen?
Yes.
Yeah. Oh, okay. Hi, I'm Shani, I'm Shani, a PhD student at the Computational and Experimental Biomechanics Lab at Tel Aviv University. One of our main topics that we conduct research is analyzing bone strength using finite elements methods. Patients with bone tumors suffer from severe pain, mobility issues, and high risk of fracture. The global market is evaluated of treatment of bone cancer is evaluated by $1.2 billion. Laser-induced thermotherapy is currently used to destroy tumors in soft tissue. We wish to expand the use to treat bone tumors. A hole is drilled in the bone, and optic fibers are inserted to the surrounding of the tumor, causing high localized temperature that kills the tumor cells. This is a preclinical study. So we use New Zealand white rabbit's femur as our model. Our main goal is to evaluate the safety of using laser-induced thermotherapy to destroy bone tumors by creating microfinite elements that will predict the risk of bone fracture following the treatment. Okay, so this is my sample, rabbit's femur, which is CT scanned with a voxel size of 40 micrometers. And then we segment the scans to subtract only bone tissue voxels, which you can see as the white colored in the pictures. I use MIA, a semi-automated segmentation method, to do this process of the segmentation. Each bone voxel is converted into a hexahedral element using simpleware. And the bottom surface of the bone is fixated. A vertical load is applied to the head of the femur, about 100 Newton. I apply homogeneous isotropic material properties, which are assumed. We assume the values of lambda and also the shear modulus. And the linear elastic problem is solved. You can see here the week 4. A huge finite element model is created with over than 125 million degrees of freedom, and this is while using linear hexahedral elements.
Just a 2-minute heads up.
Okay. This is actually how I found my way to MFEM due to its ability to handle a large model. I used a modified version of example 2P with 10 processors, and it took about 4.5 hours to solve. The main modification I made to example 2P is to calculate the strain tensor and the principal strains in addition to the displacement output, and I disabled the options of mesh refinement. The results were visualized using PowerView, mainly focusing on the displacement magnitude and the maximum principal strain. You can see here a visualization of the maximum principal strain where high values at the femur's neck and around the surrounding of the hole, it may predict fracture, okay?
You've got 1 minute.
Okay, so we plan to prove the solution convergence by using higher order hexahedral elements, and also perform experiment validation, compression tests using digital image correlations that will provide us also the displacement and the strains from the experiment and could be compared to the finite element results. We plan also to calibrate the material properties. Our main goal is to create a microfinite element of a human long bone, as you can imagine, which is a human bone is significantly larger than a rabbit bone. This will create a much larger model, and this emphasizes the need and the importance of MFEM to handle large models. Thank you for your attention.
Thanks for the opportunity. I'm Paul from TU Dortmund University in Germany. Talks about discontinuous Galerkin methods for hyperbolic problems with slope limiting and entropy stabilization. So first, let's look at the hyperbolic problem. We have a conservation law of this form where U is a vector of conserved variables and F some flux function with some initial data U naught. For example, the Euler equations, we have the conserved variables of density, momentum, and total energy. And solutions to these kinds of problems are known to lay in a certain convex set G for all x in omega and t greater or equal to than 0. Furthermore, we have entropy stability in the sense that the physically admissible vanishing viscosity solution satisfies entropy inequality of this form, which we can see below here, where eta is some mathematical entropy and q its corresponding entropy flux. And these are two properties which we like to preserve with our discontinuous Galerkin methods. We first focus on the limiter. If we assume to have a nonlinear system of the form with conserved variables, some density-like variable, and some conserved products rho times phi, we first limit the density-like variable on each element ki. With linear polynomials, we can split the local approximation into a cell average and some gradient type of term, which we then limit by this alpha, which we can see here, and we'll choose alpha such that local discrete maximum principles are satisfied at each node of the element. And after that, we take this limited density-like variable into account, limiting each conserved product such that the derived quantity phi itself satisfies a similar discrete maximum principle. And these principles are with regards to the element averages. Furthermore, if we are looking at the Euler equations, which are of this form, we take the already limited solution and limit in a second stage so that also the pressure stays non-negative. And if we do that before each SSP Runge-Kutta Euler stage, we can show that the cell averages of the next time step or after each step are then again in this convex set G.
2 minutes.
So, a nice feature of this limiter is that it's very, very easy to implement in MFEM, especially if you have the example 18, which you can take as a basis for this limiter. Now having the domain preserving property, we also want to enforce entropy stability, and we want our scheme to satisfy a local semi-discrete entropy inequality of this form, which we can see here on the top. And we do so by adding a Ruzanov type of entropy dissipation, where V is the L2 projected entropy variables. And we choose new such that we satisfy a Tadmor-like condition, an integral version of Tadmor's condition, and then we can show that this inequality holds. And importantly, the evolution equation for the cell averages is not changed, so we keep our numerical stability. Last but not least, let's look at some numerical examples. We have the scalar 2D KPP problem on the left, which is known to bring numerical schemes to their entropy stabilization limits. We can see that without the entropy stabilization, we used group finite element approximation for the flux to invoke non-entropic solution, which we can see here. And using the entropy stabilization, we can see that the spiral structure is very well captured by the scheme. And on the right-hand side, we can see a 1D Euler example where we can invoke an entropy shock in the reflection wave, which then is captured very well by the entropy stabilization to get rid of the shock.
Okay, Paul, thanks. Thank you so much.
Good afternoon from Spain. My name is Alejandro, and I've been working these past 2 years on working on the discontinuous Galerkin method in the time domain for Maxwell equations. If you can go ahead, please. So what we want to solve is Maxwell equations as discretized by Mr. Heshaven and Warburton on their book. What we're looking for is to have the flux in the strong form of the equations, which means that we're only going to have jump terms instead of just average and jump terms on them. So our work basically means extending the functionalities of MFEM regarding some things that we weren't able to find or we thought that were needed. So we're going to need some bilineal integrators with some customized jump terms for revolution time dependent operator. We're going to need total field and scatter field capabilities for illumination. We're going to need to designate boundary conditions, not only on true boundaries, but also those interior faces and edges that we'll probably talk about on the issues. We're also going to need extraction of data on specific faces and edges for some post-processing, such as radar cross-section or far field, near field. We're also going to need spectral analysis to ensure time step stability and high confidence. And of course, as we keep thinking, we find more things. If you can proceed, please. So, for example, very briefly on the bilinear integrators, we're going to have 4 main equation operators, which are stiffness. And then, as you can see on that discretized equation example for the electric field on the x, we're also going to have what we have referred to as 1 normal, 0 normal, and 2 normal terms. These operators have been defined through the bilinear integrators, the integrator forms, as you can see on the screen. And other terms, such as force functions, are applied inside these operators or as extra operators. If you can proceed, please. So the main stuff here, the main thing is interacting with you and trying to expand some MFEM capabilities in a cooperation effort. So what you can see on solid lines are what we barely touched, but we had to consider modifying slightly on the base MFEM code. And then what you can see on dashed lines are things that we have needed to implement in order to have a functioning Maxwell equation solver on this continuous Galerkin time domain, with the key thing that we needed to be explicit. So as you can see, we had to implement a submeshing method that includes boundary carryover on all dimensions. We had to implement those interior boundaries, and we also had to implement the Maxwell integrators, as we have previously discussed right now, and also other types of integrators. If you can proceed, please. So as an example of our problem that we want to simulate, total field scatter field on the following geometry that you can see that has been modeled in GMesh. And the modeling itself is fairly easy because the only thing we need to do is create the geometry. Thank you. Create the geometry, define where our boundaries are going to be through the physical tags, and then the only thing we need to do is run our solver after telling it some basic parameters like time steps or final times, the order that we want to simulate, etc. And if you can proceed, please, and play the video, that will be in the next. If you can play the video, oh, there should be a video there. Maybe you can click on it. But will it? Should it work? Well, that really was. It's okay. It's okay. I will actually share it to you, so we can maybe see it right before the questions, just so people don't think about it. This will conclude my presentation. Basically, what we're looking forward here is creating that explicit solver, so we can simulate any kind of electromagnetic problem with any kind of material and any kind of illumination or boundary conditions. Thank you very much for your time.
I'm Bill Ellis and I'm working on magnetic confinement fusion at UKAEA. Could you go to the next slide, please? So fusion's a nightmare for any materials because you're torturing them essentially. And so, high heat fluxes, high temperatures, and static and pulse magnetic fields. And so as part of our toolbox, we need to be able to model thermal expansion. Next slide, please. Thermal expansion, the GIFs aren't playing, that's okay. Thermal expansion, matter expands when it gets hot. If you try and constrain that expansion, then you cause a bunch of stresses. And if you can model those stresses, then you can better predict failure and maybe collision between components. The equation on the right here is just a linear elasticity term which is already in MFEM, which is very nice, and a thermal expansion term, which I have added on to model the thermal expansion of some components. Next slide, please. So the current solutions that are used within UKAEA are ANSYS, which despite costing $1 billion, doesn't scale very well, and MOOS, which is much more scalable than ANSYS, but has limited FE types. And as mentioned, given this is magnetic confinement fusion, it limits the use of electromagnetic problems in MOOS, given the lack of FE types. Next slide, please. So if you put the thermal expansion term that I showed into your weak form, then you get a bilinear form of the U div V and a linear form of div V, which required writing some new integrators given I'm modeling displacement in vector field, but it's like the H13 space, so it's copies of a scalar field. And having implemented these integrators, I did some quick sanity tests. So I did a simple beam model that's hot at one end and cold at the other. And what do you know? It expands where it's warm, which is, a good test. Next slide, please. And so more fun than a beam is some fusion relevant geometry. So I've got a hypervapotron here, which is this slab with two channels through it. It's just a heat exchanger pretty much, which it's got a nice name. And so with this problem, I'm modeling the fluid flow through these channels, which would normally carry all your heat away with some cheap convective heat transfer boundaries. And then I've got some Gaussian heat distribution across the top and some fixed displacement boundaries on the bottom of the hypervapotron. So this is the model we'll be using to, have a look at our thermal expansion terms. Next slide, please.
2 minutes, heads up.
Coolio. This is what it looks like when you model thermal expansion. It goes a bit bendy. That's not very interesting. Next slide, please. More interesting bits are the solves. So I'm currently solving in 4 ways. One of them is the MOOS way, I've called it, which is basically you solve for a temperature field and then you solve thermal expansion as just a purely linear form. Or you can do it like I've done it in MFEM, which is doing it in one big monolithic matrix. It's a bit more tightly coupled in terms of the physics. So yeah, that's preferable. Next slide, please. So when you run these simulations, you see that things are looking pretty good for MFEM. The MOOS and PETSI solves show the longest solve time for the linear solve step and the highest number of iterations required. And strangely, the analogous MFEM PET2Solve, which does it in the Moose way by solving for a temperature field first, and then solving expansion, thank you, as a linear form. Despite creating almost the exact same operator, takes a lot less time to solve. I believe this is because MFEM is better applying boundary conditions and is allowing a couple more terms in the operator to be zeroed out. And then, best of all, you've got your MFEM and hypersolves, which is good to show because I'm an MFEM workshop and not a Moose one, so I'm happy that that's performed the best. Things are looking pretty good. This should be nice in terms of integrating it with some of our electromechanical, I can't stop saying mechanical, electromagnetic solves, and coupling in some thermal expansion terms in that and seeing what happens to some fusion components. Next slide, very quickly, please. So yeah, things are looking good so far. I need to do some further scaling testing. I tried with a model with more elements, and LibMesh and Moose had a bit of, they threw their toys out the pram, so we'll have another go at that. And I need to do some GPU testing and some nonlinear mechanical formulations as well with this. But so far, it's looking pretty good. So yeah, thank you.
Thanks so much, Bill. Before opening the floor for questions, I would just say this is a new thing, and I'm impressed. Great job, guys. Very specific, goal-oriented, and mentioning MFEM a lot in a positive way. So thumbs up. And now, yes, sorry, not guys, everyone, do you have questions?
I have a question for Shani.
Yes, please.
Disappeared for a second. I'll wait. Can you hear me?
Yes.
So you mentioned that the solve time was, I think you said 4 hours. That seems like a long time. Was it a lot of iterations? Was it each iteration was expensive?
There was a lot of iterations, and yeah, I don't really know why it took that long time. I'm actually in the process of understanding how MFEM solves and why it has such good capabilities to solve large models. So, but yeah, it had a lot of iteration, and also the time between each iteration, I think, was quite long.
You should be able to do better than 4 hours.
Can I ask a related question? Like for an elasticity problem at that scale, you kind of had a lot of elements from my experience. Was the reason is because you were just associating each element with a single voxel, or did you think you needed that many elements to resolve the physics or something?
This is how this is how you create a microfinite element. This is the procedure. Each voxel of the microCT, which represents a bone voxel, is converted to a hexahedral element.
Yeah.
This is the procedure.
All right. Next year, I hope to present on something that might help you there. But anyways, we'll see if it happens next year.
Very impressive work. I really enjoyed it.
Thank you.
Thanks for the questions. Other questions? I will have one question for Bill. So you mentioned it's important to have a variety of finite elements for MHD or for magnetic fusion. Would you develop a little more what you meant?
So in terms of like the variety of kind of spaces which you can effectively model. So like when we've used Moose for stuff, it kind of gets confused between the description of the mesh and the description of the finite elements themselves. There's not a very good distinction, and having a better distinction with that in MFEM allows kind of for us to solve kind of the EM problems in more efficient ways and just more difficult problems, really. I'm probably not the best person to ask about the EM itself, more on the mechanical side. But yeah, it's a lot about the distinction between the mesh and actually the elements which you want to live on that mesh.
All right, so a follow-up question: what's better, Moose or MFM?
I think you know the
I think there's space for both, just so we're clear.
No, there's only one answer. So far for me, MFM, but I take no sides. Yeah, you know, in diplomacy.
Yeah, thanks, Bill. I would say that
Cooperate and
the
work
abstraction of
together.
MFM is good, so it helps. Other questions?
Yes. Can you hear me?
Yes.
Yeah, just a follow-up. So forget about the different teams or politics involved. Scientifically, what is the distinction between the two approaches fundamentally, or math or physics or whatever? Moose versus FA.
Is this a question for me or for the MFM?
Whatever, yeah, either of you guys, you can help to share some light, that'd be good.
In my presentation, the difference was really the creation of the operators, like your A matrix itself, and the underlying solvers I was using. So MFM has access to some of the hypersolvers, which enabled kind of better performance with my solves, and also MFM was better at applying boundary conditions. It was able to zero out more terms than Moose or Petsy or libmesh, whatever part of it was doing the application of the boundary conditions.
If I understand you correctly, you were basically saying algorithmically, one has less amount of computation than the other.
In part of, yes, kind of, but in a kind of specific instance of what I was using it for. This might be better for the MFM team to take over for, though.
Sorry, I will actually slow down the discussions here now, because we want to continue with the second half. But yes,
Okay.
Please keep the questions for the discussions after the sessions.